All right. Well, I want to welcome the folks that are joining us here in the room and those online. This is your first time joining us. My name is Scott Williams. I'm the Research and Education Coordinator here at the Wisconsin Energy Institute. And I coordinate the Sustainable Energy Seminar Series, which we hold every other week here at the Wisconsin Energy Institute and online. Our goal for holding these seminars is to highlight the cutting edge research from across UW-Madison and beyond, and to showcase how different disciplines understand energy challenges and develop sustainable solutions. Throughout the series, you'll hear from experts in science and engineering and social sciences and humanities to get a more diverse perspective on the different energy challenges and sustainable solutions and how different disciplines understand those challenges. The seminar is open to the public, but is also a class for the Certificate in Engineering for Energy Sustainability, as well as the Sustainable Systems Engineering Master's Program. We do have this seminar as a hybrid format. If you're joining us online, please use the Q&A to ask any questions. We'll also get questions from the folks in the room and maybe go alternate between in-person and online questions during the Q&A time. We do have live captioning for folks online. You can click on the show captions button to use that feature. With that, I'll introduce our guest speaker today. Jim Tingham is an associate professor in the Civil and Environmental Engineering program and the director of the Geological Engineering program here at UW-Madison. He's responsible for outreach, research, and engineering education in the areas of geotechnical, geoenvironmental, and energy sustainability, with an emphasis on transmitting practical research applications directly to the engineering community. He established the UW-Madison Geothermal and Energy Geotechnics Research Group in 2010. And for about a decade, he's been working with Epic Systems on instrumenting their geothermal exchange system and understanding the characteristics of that system, which we'll talk more about today, as well as what the knowledge gained from that research means for future district scale geothermal systems. So welcome.
All right. Thank you, Scott, and very pleased to be here. And for all of you online also, I will pace around a little bit. So I'll if I point to something, I'll try to use this magic pointer, but we'll see. So district scale geothermal opportunities and challenges for one of those energy resources that you probably don't think much about, but I'm going to put some scales out there for perspective on what large-scale geothermal can do, and I'll be using the Epic Systems campus as my focal point, the largest geothermal exchange system in the world, to my knowledge, and also our progression towards similar projects at West Point, Detroit Arsenal, Ford Motor in Memphis, Tennessee, and other places. Just kind of start with something inspirational, and I'm not going to do the Massachusetts accent, but I like it. We choose to go to the moon in this decade and do the other things, not because they are easy, because they are hard, because the goal that will serve to organize and measure the best of our engineers' energies and skills, because that challenge is one that we are willing to accept, one we are unwilling to postpone, and one which we intend to win and the others too. So we can do this whether you care about energy resiliency, greenhouse gases, and global climate change. This is a challenge that we are up to, and we in society can do with people like us in the room. So those challenges of carbon sequestration, energy storage, green hydrogen, and the list goes on. We're at that ground level, and I know that we can get there. I will mostly be talking about energy storage. So this is a little bit of a screenshot from energy data that I get daily from Epic systems. Their flows to their different bore fields, through their heat pumps, their chillers, their energy usage. Epic Systems is a very gracious research partner, allowing myself and my students access to this information so we can poke and probe and look at it and calculate coefficients of performance and payback and environmental assessment. Because when you can measure what you are speaking about and express it in numbers, you know something about it. That's Lord Kelvin. And I know sometimes our political system can measure things in different ways, but we as engineers and scientists, really expressing it in numbers, having hypotheses, testing those hypotheses, trying to remove the bias out of it and answering those questions. Just earlier this year, Madison City Council was looking for new rules for big buildings. So why did I put this here? So if we don't measure where we are in our energy consumption in our big buildings, how do we know where to go to? So lots of pushback there from businesses and developers and similar, but one of those things that is gonna go to a quote from me in an article that was used to promote this. So this is Tingem. The most logical application for geothermal heat exchange is in district heating and cooling systems, serving campuses, industrial parks, and neighborhoods. For example, a city could require or incentivize developers to put well fields into new subdivisions, allowing homeowners to tap into those energy savings. All right, so first, what is large-scale district heating and cooling? And simply put, it is a commonly or a community well field is where we are exchanging heat as a community, almost as a utility for heat and cooling per se. And that community geothermal exchange is then meted out to people that are on that community or district scale system, buildings, homeowners, factories, whatever the case may be. So instead of every one of these individuals investing in their own geothermal exchange system, we share that community resource and we put the heat pumps and the chillers in the individual buildings, but we're using a common high efficiency geothermal exchange field. Maybe that geothermal exchange field is in a city park with soccer fields on top of it, or a common area, whatever the case may be, where we have that space to put these large systems that we're going to be talking about. All right, so let's talk about scale. Like geothermal, in that it scales very well, very unlike wind energy that I've also been working with for a decade plus. But wind energy just does not scale well to the residential scale. You're not going to have wind at your house unless you're just an enthusiast and want to lose money. Wind energy works best at large utility scale, 100 megawatt and above. It's where it has its efficiencies. Not so in geothermal. Well, yes, there's still efficiencies of scale, but it's not as pronounced. So let's look at residential scale first. Typically, your capacity is 2 to 8 tons, less than 10 geothermal exchange wells. Cost typically well under $50,000, and say about $75 plus per meter of installed geothermal exchange well, with the coefficient of performance of 4 to 6. So first, let me define coefficient of performance. Coefficient of performance means that for every 1 unit of electrical energy that I put into the system, I get 4 to 6 units of heat or cooling energy out of it. Okay. So yes, geothermal exchange uses electricity, and electricity's got to be generated somewhere, but you get 4 to 6 units of energy out of it. So let's just compare a coefficient of performance of 5 to your natural gas furnace. The highest efficiency possible for your natural gas furnace is 1. Okay, you burn 1 unit of chemical energy and that goes into heat. It's the highest possible you can get out of a heat furnace, out of something that's burning something is 1. So we're multiple times more efficient than burning a fossil fuel. On the cooling side, we're about twice as efficient as a traditional air conditioning system, whether it's cooling towers or some other type of system. That's going to matter later when how we think about this for energy resiliency. All right, so let's start with that residential, and this is the heating cycle. So what we are doing is typically, my rule of thumb, general rule of thumb in this area is about, say, about 60 to 70 meter deep wells. Every 60 to 70 meter deep well will give you about 1 ton of capacity. A typical residence in Madison has probably a 3 or 4 ton system in their house. So a typical resident might need 3 or 4 60, 70 meter deep wells to provide the heating and cooling in their house. We are looking for delta of about 3 to 5 degrees Celsius. So what that means is in the winter, I'm putting cooler fluid into the ground, and the earth is being used as a thermal battery to warm up the water in that pipe and bring it back about 3 to 5 degrees warmer than when I put in. That's our energy exchange. So that's our power moving mass, which is our water, times by the C sub P, or the storage term of water, times by T out and minus T in. That's our power. That's thermal power. That's actually the definition for thermal power. All right, so that's the geological part. Going into our formation, this general, running through a heat pump. In this particular one, the heat pump is a water to air, because we're supplying hot air in this particular case. It also can be water to water. And if you have a diesel heater in here, you also can get domestic hot water out of the system, especially in the summer when you're trying to get rid of heat. Put it to your domestic hot water versus putting it back into the ground. So that's it in a nutshell. Hey, this is not rocket science. No, we don't have to send somebody to the moon. This is doable, and we've been doing this. All right? This is some mechanical engineering, some geoengineering, but very, very doable, and has some limitations. We'll talk about that. But now let's go to commercial scale. Say 10 to 100 tons of capacity. Maybe we got tens to low hundreds of geothermal exchange wells. That where our scale is going to get us is here. Usually we're going to get a better drilling price from those contractors because they're there for days and days drilling. So this is where the scale matters, is the geothermal drillers can give you the best prices because they don't have to mobilize here, and the next day they're over here, and the next day they're over here. So this is an example of the system at Badger Rock Charter School here in Madison, just south of the Beltline. So Badger Rock Community School, they have geothermal heat exchange at their system, and they have 72 wells, 300 foot deep, and that is used for Badger Rock as an example of a commercial or building scale on geothermal exchange. A little bit bigger pumps for that system. So you see the, can't count all of them, looks like 4 pumps, but you always have at least 1 pump and the second pump for backup. So then the scale also is we can also more efficiently pump our loop we get higher efficiencies out of bigger pumps and variable speed pumps and similar. So that's the commercial scale. Now, let's go to the campus scale or the district scale. Pun intended, I'm going to call it the epic scale. All right, so this is epic. Hundreds to thousands of tons of capacity. You're going to have well over 100 wells. There's actually about 6,500 at epic. Well over $1 million for those well fields. You're going to get the most economical, maybe $60 per meter of geothermal exchange well, and a coefficient of performance pushing 7 to 9. Depends on how you count that. I'll show you another couple of really cool things about this. So these are just stacks of heat exchangers. One to the next, to the next, to the next, to the next, and then there's another empty row here. So this is a centralized heating and cooling plant at Epic, ready for growth. You can put more heat exchangers in there to plan for that growth. And one of my past graduate students there, this is multi-stack, and this is a chiller. This is a maglev chiller, the highest efficiency chillers basically in the world that we're using, where instead of bearings that support the rotating compressors and similar, it's maglevs. So on the mechanical side, instead of using ball bearings and similar, we're using magnets to rotate that with the least amount of friction possible. So that's why these are so energy efficient. We can't put them in our houses yet. The technology is not there. It's too expensive, but we can do this at the large scale. 915 tons. That's a huge. It's just a huge piece of equipment. Really can move cold water in a hurry. And guess what? Multi-stack. These are made in Sparta, Wisconsin. Okay, so domestic manufacturing, domestic energy systems made right here in Wisconsin with multi-stack. I think that's pretty cool. All right, so just a little test or quiz. I think Alicia's seen this before. So, are all watts created equal? So Scott can monitor the online crowd, but who would put a check next to JJ? JJ, who's the favorite? Oh, we might have a winner. We got 2, 3, 4, 5, 6, 7, 8. All right. How about Derek, the little brother, fullback? Yeah, nobody loves the fullbacks. All right. How about League Defensive Player of the Year, Pittsburgh Steelers, TJ? Anybody got TJ as their favorite watt? All right, well, JJ, apparently, big brother, is taken away. But I do have a point to this, okay? My point is, now let's go to power. What's your favorite watt? Thermal, radiant, electric, or chemical? It's a rhetorical question. If you were in my sustainable energy course, we'd take a vote on this. But I can guarantee you that a watt is a watt is a watt is a watt. There's the same amount of energy in a thermal watt as there in an electrical watt, but it's what we determine to be useful for us. Heating and cooling, that's useful energy. Electricity to run this projector, that's useful energy. Chemical energy in a battery, that can be useful. So, but a watt is a watt is a watt is a watt. So really, in geothermal exchange, we're looking at kinetic energy. Thermal energy is a form of kinetic energy, and that's what we're utilizing in our energy, and that's what we're storing is thermal energy in these systems. All right, so that energy exchange rate, there is the equation. We got the density of the exchange fluid, the specific heat capacity of the exchange fluid. EPIC, it's water. Okay, there's no chemicals in that system. It's purely water. Change in temperature, the flow rate of that fluid, and we integrate this at EPIC every 15 minutes, and we've been doing that for almost 10 years, just tracking how much energy is out there. This is a circuit. Hard to see. I don't know if we can turn this front light out or not, or we'll just leave it as is. So this is a circuit. Typically, there's about a dozen to 15 wells on one circuit. There's another circuit. These wells are about 6 to 7 meters apart, 152 meters deep. And we just have lots of circuits at a big site. But generally speaking, commercial scale, EPIC scale, we're just doing these circuits of water. It's not complex. Have a bigger pipe going to a slightly smaller pipe, going to a slightly smaller pipe, going to a slightly smaller pipe, and that's moving the water through the system. The smallest pipes in our system are the vertical columns. And we got some up to, I can't do the conversion in my head fast enough, but we got about 36 to 42-inch headers out there bringing this home. All right, so EPIC systems. I don't know when I stole this from Google Earth, or but it's probably built like 5 buildings since I've done this. But medical software company, a dominant position in the US market, European market, and elsewhere. 10,000 employees, campus that we've all heard about. The entire campus, heating, cooling, domestic hot water is all from geothermal exchange. There's no backup systems there. They're powered by geothermal exchange. They got some spare heaters, and I think in their auditorium, but that's it. Entire campus heated and cooled with geothermal exchange. Also the domestic hot water. Also, they have some snow melt operations from some excess heat. So if we can do this for a 10,000 person campus, we can do this for universities, definitely for high schools, middle schools, corporate campuses, the Amazons of the world. This is very doable if we can do it here at EPIC Systems. All right, so I was introduced to EPIC in 2009 by a colleague of mine. Her husband works at EPIC, and she goes, yeah, did you know that EPIC is using like this geo something out there for their heating and cooling? And I go, no. She said, hey, can you get me a tour? And so she talked to her husband. Her husband connected with the facility manager at the time. His name was Bob Brandherm. Came out and he goes, nobody asked to come out and see this. You're like the first one. And he showed me the system and I go, this is awesome. Why doesn't anybody know about this? And I said, well, his actual quote was from the owner or the of EPIC, and it says, we do things because it's the right thing to do. And it's evolving a little bit. But so I then got invited to have a large research collaboration on their largest geothermal exchange field. It's 2,596 borings. I know because I sent Alicia out there to count them. No, just kidding. That's what it says on the design sheet. I've never actually counted them. But we've been running this for over 8 years, every watt into and out of that system and the energy it takes to run that system. We've been tracking and trying to make the most sense out of it. Those 4 geothermal exchange fields, GHX, by the way, Geothermal Heat Exchange, 48.5 megawatts of thermal capacity. If you add the heat sink pond and the deep quarry lake, it's 92 megawatts. So that's a large system, actually the largest system. This is what that field looks like. So here's the geo side of it. We're going through the Prairie du Chien group. It's crap rock. That's what the geologists and the drillers call it. It's got karst in it and things like that. The drillers don't like it. Going into the Jordan Formation, a beautiful quartz sandstone. St. Lawrence Dolomite, Tunnel City Group, Wanawak Formation, and into the Eau Claire shale. So really nice test bed of a sedimentary basin where we can track heat flows. And the beautiful thing for us as a researcher is every one of these formations has different thermal properties. So it makes it really cool to try to figure out where all that heat is going across very dissimilar geological media. And then the other thing why geoscience and geological engineering is so hard, because we work with geologic porous media. So porous media, variably voided. Voids sometimes are filled with air, sometimes where they're with water. So it can be challenging. I've got 2 test wells here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Got 11 wells out there where we're monitoring temperature development. And we're putting in a couple more down here, I believe, in the spring. And EPIC will be expanding in a new field at some point in the future as their campus keeps growing. All right, so let's look about that. So from 2015 through September of last year, we've been tracking how much energy has been exchanged in just field 4. So just that one field, not the entire system. But we could do that if we want, but little baby steps first, stick with one field. So terajoules, yeah, shoot, tera. Is that to the 15th or the 12th? I can't remember. On scientists and engineers, it's 12, tera, then 15 is peta or exa, then peta, okay. Yeah. It's a whole lot of energy. A terajoule. Joule is this little tiny, inconvenient little tiny unit, but we had terajoules. So they had excess heat the very first year. They were mostly dumping heat into it, also into the second year. And you'll see a couple of things that if you're scientifically oriented, you just go, wait a minute, we're putting a lot more heat into the field than we're taking out. And that's the case, because even in Wisconsin, most commercial facilities are cooling dominant. We, as humans, are releasing heat, got the lights, the equipment, computers, servers, they're all generating heat. So most commercial, well, I'm going to almost say almost all commercial scale facilities are cooling dominant. So we actually have excess heat that the field has to absorb and dissipate to some degree. Something we're working on. Just by the way, I don't know if you read that article. I had a beautiful quote. The biggest battery on Earth is the Earth. We can store a huge amount of energy in the Earth. It's just a huge thermal battery. And that's what we're doing. So simply put, if you had to explain this to your parents, your sister, your uncle, whatever the case may be, what is geothermal exchange? We use the Earth as a thermal battery. In the summer, we're putting heat into the battery. In the winter, we're taking heat out of the battery. We do that more efficiently than typical heating and cooling systems. That's where the payback is. Then just January to February, a couple of things that even in January, at times, EPIC is in cooling. Hour over an hour, there's maybe the late afternoon, everybody's on campus. Even in January, sometimes they're dumping heat. Not all of it goes into the fields. You know, the excess heat is moved between buildings. So if one building is using heat and another one is cooling, they're not putting it into the field first. They're just exchanging it between the buildings. There's lots of mechanical complexities. What basically our mission at EPIC is the least amount of push necessary to provide the heating and cooling. So if we run it all the way through the fields, we've got more push to exchange that energy. If we just have to go from this building to the next, it's less push on the system. So yeah, so August and September, lots, all July, August, September, purely cooling. We're dumping heat. And Alicia is one of the graduate students looking at where that heat is going via modeling of this complex system. All right, so the average was 81 terajoules in a year for just field 4, just that one field. That power is equivalent to 6,900 people driving a Tesla 3 for a year. Same thing. Energy equivalency of 2,650 households, their electrical use. So running this field is the same amount of energy as all the residents in a small town or medium-sized town such as Wapaka. That scale of how much energy exchange is occurring. Oh, there's Wapaka. I did this out in Stanford earlier this year. So we had to show them where Wisconsin was and definitely had to show them where Wapaka was. So for the equivalency. We go every year, usually we go to the Stanford Geothermal Conference in January, or no, sorry, February, because who doesn't want to leave Wisconsin in February and go to California? All right, so a couple of things where we have a very rich data set. We use fiber optics, so all of those 11 wells that are out there, we've got fiber optics down the hole. So, Tinjum, why in the world would you put fiber optics down a geothermal exchange Century well? Well, it turns out that when I shine a light or laser through that fiber optic, it interacts with little imperfections in that fiber optic crystalline structure. And some of that light energy will come back. We know the speed of light. So I'm measuring these signals bouncing back, and I know exactly where that scattering event happened. Okay, well, that's cool. You know where all the imperfections are. But even cooler is we use the ratio of the waves, the scattering event, which are perfectly correlated to temperature at the point of correlation. So what this means is I've got temperature from basically every meter of fiber optics, and I do it about every 20 minutes for 8 years. Well, except when it was down during COVID. But anyway, so what we call this is distributed temperature sensing. So with the 11 wells and this 1 meter sensitivity, I get a 3-dimensional view of where the heat is or what the temperature is in the field. So a couple of things that we see, and here's one of the Century wells, is we've had about a maximum 4 Celsius increase after about 7+ years of operations. Makes sense because we're dumping a lot more heat into the field. So the field is heating up. So my research is developing techniques where we really understand the geothermal properties first before we design a field, so that we design a field with the appropriate capacity that does not overheat. Because if it overheats, like Ball State is one campus that was poorly designed and operated. If it overheats, the efficiency goes down. And if it overheats significantly, you might also have some ecological impacts One of the hypotheses was is there going to be arsenic release if you overheat the field? We actually did a research study with the DNR and said no. Where we're operating, it's not even close to doing the significant enough temperatures to get an arsenic release because of enhanced chemical reactions at higher temperatures. So, not with rocks. If it was like a clay soil, there could be some consolidation thermally impacted, but not at 4 degrees Celsius. I don't want to say it's incidental to the field, but it's pretty close. But irrespective, you want to keep it sustainable for the long term. Different well, a little bit different. We had about a 5-degree maximum Celsius, 5 Celsius increase. And you see a few other things is that it is seasonal. It heats up in the summer, end of summer, cools down a little bit, heats up again. And this is pretty common for geothermal exchange systems worldwide. So are the fields heating up? Yes, a little bit. Another one of my graduate students is looking at the impacts of this to the coefficient of performance. We want to know, okay, how much has the coefficient of performance changed? Because now we got to push a little harder, push a little bit more water, a little bit hotter water to get that same delta. So we're looking at that. And a brand new thing that we're doing, another graduate student, Shubham Atri, is actually teaching 367 now for the campus. We're using machine learning. So a lot of people across the country have said, hey, you've got great data, but so what? It's like, okay, how are you going to use that? And so we're just on the ground level of using machine learning. As the start, we're looking to hindcast. So this was our challenging years when our interrogator shut down and then COVID happened and we couldn't fix it for 1.5 years. So as an example, you hear about machine learning all the time. Maybe you've got projects on it. So what it means for us is, my analogy is how do you train your dragon? Or in our case, how to train your geothermal field. So I have that rich data set I have, and this is just well temperature at one spot at one point in the field. So I got like 10,000 of these graphs possible. So, and then I've got flow rate, and then I got change in temperature. And then we got electrical energy going into their campus centralized heating and cooling. And so what we want to do is train our dragon using existing data so we can predict what will happen in the future. Okay? So we're training our geothermal field or our system. So I go, what if I delay putting well field 5 for 5 years? What will happen? What if I put well field in next year? What will happen? What if I put more energy into field 4 versus 3? What will happen? So our goal is with machine learning is to take this rich data set and then train our system to be as efficient as possible and do those what if scenarios. So instead of just saying, let's put in another 2,000 wells and let's see how it goes, hopefully make some educated decisions about how these will impact our efficiency of our system. So in this case, we're taking to do that hindcast here. So we have that little bit under 2 years of data that's missing. So we're using exponential smoothing for time series predictions. And so the blue is our well temperature, and then we got the forecast and the fitted. And so we're basically using existing data. And that existing data includes ambient temperature, ambient humidity, all of those types of things. We're putting all the variables in there to try to figure out which variables are significant for our machine learning. Okay, so we've trained it pretty well. Pretty much anybody can do this. If they have data and they spend enough time, you can recreate it, but that's what you have to do. You got to train your system against your data. And then we are using Holt-Winters triple exponential smoothing for the prediction. And just because it sounds cool, Holt-Winters triple exponential smoothing. And we have an abstract accepted on this, where we're basically minimizing our error. And remember I said we've only been doing this for a couple of months. So then we did our hindcast, and we said, okay, we take all of that data, and we have the data here. We have the ambient temperature, flow rates, and similar. I just don't have the field. And this was what we would have predicted. Okay, looks good. We're a little bit off, you know. So we're still working on it. Okay, so we're working on just huge amounts of data. So then once we nail down this hindcast, then I can change my parameters over here and say, okay, what if we do this? I'm much more confident that we'll predict what will happen to the field using machine learning. Yes, sir.
You said that you were using the real flow data or just the real ambient data?
We're using everything. So I'm using meteorological data for Verona. So temperature, precipitation, wind speed, humidity, because I don't know what is important or not. And then I'm also using flow rate to the field, temperature into the field, and temperature out of the field. Probably a few other things. Do you have a question, sir, or just stretching? Okay. Yeah. So I've got that data. And in this case, we're just training it for the field temperature. But in the future, we can train it to predict change in temperature going in and out, which impacts the performance of our chillers and our heat exchangers. So yeah, so we're working with a colleague at St. Louis University that's an expert on this. And I said we're only a couple months into it, but that's where we're trying to take this data to do the what ifs. What do I got? About 10 minutes left? Okay. All right, so the other thing is we have excess heat. I know that we're putting excess heat into the field. Where is it going? So a simple heat balance, and I know how much heat is going into the field because I'm measuring the flow rate in, the T in, and the T out, and I have all the temperature in that three-dimensional box. So this is the heat going into the field, cumulative, and it has that winter, summer, pattern. But you see that we have put in an excess of almost 400 terajoules of heat into that field that have gone somewhere. The storage term, this is the field heating up. Okay, so I have that volume and I've increased 4 degrees Celsius. I know, okay, that's how much that change in heat of the field is. And then I know that approximately 200 terajoules has gone somewhere. And so that's what Alicia, that's one of her topics is, okay, has that gone laterally? Has it gone with the groundwater out of the field? Has it gone through the bottom of the field? Has it gone out through the vegetative cover? Has it been lost to the atmosphere this way? That's where we're going next to try to, okay, I know how much energy has disappeared. Now we're trying to figure out, well, where did it go? We are putting some wells next spring down gradient to help us with that. And then Alicia is doing COMSOL modeling to try to use analytical predictions in a COMSOL model to figure out where that heat is going, because that will help us design fields in the future if we just know what the heat balance is and where that heat goes or where it stays and similar. So another project that we got. And in this last 10 minutes, I just want to bring an analogy. And so EPIC also has 10 megawatts of wind, got 2 megawatts of solar. And I realize I'm an engineer and I use different scales on my axes, but their wind system is bigger than their solar system. But we talk about complementary energy. And my hypothesis is that solar and wind and geothermal can be very complementary. So utilities and certain people don't like renewables because they're not dispatchable. You know, that big word is, well, I can't count on you in August 30th at 5 o'clock p.m. to give me the power I need, that big term. But if we use complementary energy, we can get there. So just as an example, time of day, wind typically in this part of Wisconsin peaks in the early morning hours and then late in the evening. And solar obviously peaks at about 3, 4 o'clock. So just in that alone, if you have wind and solar, and these are just 2 small sites, if you compiled hundreds of sites and hundreds of solar sites, this would be even smoother. So in Wisconsin, over time of the day, solar is providing energy when wind isn't, or as much. So they're very complementary. So how do I explain that to my family? Well, I use Reese's peanut butter cups. Okay. So chocolate, say wind, that's good. I like chocolate. The peanut butter, maybe the solar, I like that. You put them together, now you got something. Now you got something. So I think wind and solar and geothermal can be very complementary flavors. So then this is just month over month. That's the other thing is in the summer, the wind energy is worse in August, and it's peaking in June and July for the solar. So also very complementary month over month, wind and solar. Okay. Again, Reese's peanut butter cups. Now, my vision and what they're thinking of at Princeton is now let's put geothermal exchange in there. I don't know if this is the entire site or field 4, but when solar is most pronounced, that's also where we're using the most geothermal. Remember I said that geothermal exchange is about 50% or twice as efficient as a normal system. So if I didn't have geothermal exchange, I would be using twice as much electricity for that cooling. I'm using less, and it's also time coincidence to the solar when I need that extra energy. And now let's think about how do we load shift? So now we go, hey, why don't we make cold water from geothermal in the early morning hours where electricity is cheaper for industry scale systems. And then we use that chilled water here where we have peak energy demand. Energy is the most expensive. That's another type of thermal battery. Let's use geothermal. Let's make chilled water when it's cheap to make chilled water. And then let's use it later in the afternoon. Very possible. Princeton is doing this. I think they got about a 2 million. And there's purchase power at Epic. It's a little bit flipped. You would think that a cooling dominant campus would have peak electrical demand in the summer. Actually, it's the reverse. Epic's peak electrical demand is in the winter when they're using that electricity to make heat. So Epic, instead of burning things to make heat, uses electricity to make heat. So they're flipping the script. Their peak is in the winter, typically when electricity is much more available, because all the power plants are more efficient in the winter, as an example, and we don't have all of those cooling systems. So just some food for thought that we're flipping the script on energy resiliency and where our peak loads are. So yeah, can we use geothermal to shift load? Absolutely, we're doing it already. Natural gas, so just instead of burning natural gas, we're using electricity. We're using more electricity in the winter, but we're using more electricity in the winter because it is more highly available and it's cheaper in the winter. Your power plants, we build more power plants for summer peak load, not from winter peak load. All right, just I think 2 or 3 slides left. What's next starts now. We have a favorable federal government by executive order looking to catalyze clean energy industries with federal sustainability, especially solutions for groups of building versus building by building. As an example, I'm working with the Department of Defense. They own 300,000 buildings across 500 installations. 33% of the Department of Defense energy use is for heating and cooling these buildings. And so if we can be more resilient, more energy efficient on purpose for a large institution such as the Department of Defense, we're looking at thermal microgrids that integrate energy storage, ground source heat pumps, ultimately leading to significant reductions in energy, significant reductions in greenhouse gas, and the higher upfront costs are offset by annual operational savings. Ford Blue Oval campus outside of Memphis, Tennessee, we proposed a fiber optic system to monitor their cooling only system over top of a large aquifer. We have funding from Oak Ridge National Lab. We're just waiting for Ford to sign off on it so that we can go put our system in, paid for by one of our national labs. Princeton has university-wide policy to be carbon dioxide neutral by 2046. How are they going to do it? Geothermal exchange. That and chilled water is how they're going to for their mandate to be CO2 neutral by 2046. And finally, one of my projects at Appleton International Airport, can we use places like the airport to do community geothermal, where we then meet this out to your tenants at the airport site, such as FedEx, Bombardier, or similar. Again, this would be a community scale system. The airport would own it, and then they would act as, I will give you hot water or warmer water. You put in your heat pump, and we'll use this community system that I will invest in, I will install, and we'll have to figure out how that payment happens and things like that. But those are some of the things that we're working on here in Wisconsin. Lots of thanks. Lots of companies have put in time, materials, and drilled the wells for us and things like that. Lots of graduate students. And I believe I am there. I'm easy to find. I'm the only Tinjum on campus, probably in Dane County. There's a few more of us in Wisconsin, but jmtinjum@wisc.edu. And happy to take some questions or comments.
Question back there?
Yeah, I'm kind of familiar with the EPIC sites over there. I worked with some like drilling stuff over the summer. How does like void space have an effect on the geothermal stuff, or is it like fairly negligible?
So rock is a porous media, and more porosity of the rock, the more it's going to transmit groundwater through it. So the porosity directly impacts what we call advective heat transfer. So if you got groundwater flow, you're moving heat by advection instead of convection. So if your groundwater just sits there and doesn't move, you're only moving heat by conduction. If you add groundwater flow, it can remove a lot of heat via advective. So, and then the porosity of the rock also then impacts how much water is in it and how much water moves through it. So we have a zone in that upper Dolomite that's very karstic, and we know that a lot of heat is moved through that system because it's karstic. And so that part of the field stays cooler than all of the rest of the field versus the shale at the bottom of the field that does not transmit water very well, heats up the greatest because it has the worst thermal properties and the lowest hydraulic conductivity. Here first and then there.
So have you tracked any like offset, like carbon mass offsets from some of the energy saved in the project?
Yeah, we have. So we have published one life cycle assessment paper specific only to field 4. And so basically we have calculated that it takes 1.4 years of energy of use of the system to pay back the embodied energy it took to build that field. So you got embodied energy for the plastic, and the manufacture of the plastic, you got to transport the plastic. We counted all of the diesel that it took to drill the wells, the sand, the bentonite. And so yes, it's not free. Our field, we calculated, would be paid back environmentally in 1.4 years of operation.
Yeah, on your first slide, you mentioned that there are some limited nuclear decay reactions in the ground.
Yeah.
Could you go into some more details about those?
Sure. So why is the Earth warm? It's not just stored energy from the formation from cast off from the stars back in the day. Part of the reason the Earth is, primary reason the Earth is warm, because there are millions, if not billions, of small nuclear decays occurring naturally. Every one of those decays releases a small amount of energy. And the Earth stays, it keeps that temperature because we have like a blanket on it. And so if you have a little nuclear decay occurring a kilometer down, that warmth stays there for hundreds, if not thousands of years, because the Earth is a good insulator. But yeah, so in generally, our Earth is warm because of just billions and billions of small little nuclear decay events through the entire mass of the Earth. Yes.
And is the presence of radon related to that?
Part of it, yeah. So there's radon is a nuclear is a decay event. And so not only will radon get into the basement of your house, but it also releases a little bit of heat when that reaction occurs, when we make radon gas here and then there.
I was just wondering are you guys tracking the number of people, and does that have an impact on the load? And like, is the EPIC campus increasing in the number of employees? Could that also help explain an increase in temperature? And maybe the lower prediction?
Yeah, you're thinking well, and I haven't asked for that data yet. I'm not sure if they would give me that data, but I think that we're off on our machine learning because COVID upset the balance of people in the buildings.
Right, yeah.
So we taught the Dragon pre-COVID. So actually we're just trying to figure out, okay, there probably wasn't as many people on campus. They weren't using the systems the same. So that's just one of the things with machine learning. Things change. Are you thinking about that? And haven't got there yet, baby steps. Yes, sir.
I'm assuming that you're developing empirical heat transfer models to but actually predict how well these fields will operate and how to design them. So I'm kind of curious that after doing that, how are you going to share that with the industry in general to allow them to, gain more accuracy in developing?
Yeah, so good question. So yes, the design of fields right now is basically doing a thermal response test for a single well. So you can basically get the bulk thermal properties of that well, and then we're using analytical simplified solutions to design an entire field based on that one well. That's current standard of practice.
So they actually did drill one well to get some data?
Yes.
And then go from there?
Yeah, so generally we'll drill a well, put hot water into it for 48 hours and measure T in and T out and flow rate, and then we can get into that bulk. And then the standard of practice developed at Oklahoma State and International Ground Source Heat Pump Association then is to take that, and then they'll do temperature penalties based on how close you put your wells. What I want to do is do direct calculations with distributed thermal properties and groundwater movement to improve those forecasts. The other thing that those models don't do is they'll tell you what's going to happen on day 1. They're not going to tell you what happens in day 10 or day 10 years. So but that's a lot of computational power and money that has to go into that to get there. But that's why we have graduate students.
Yeah.
So we got a few questions online.
Yes. You want to repeat one?
I can read it. Yeah. Read down the list. So Raj asked, do you consider using absorption chillers for using the excess heat?
So I'm not a mechanical engineer. I'm a civil geo side. I know how they operate, but I allow the mechanical engineers to make those decisions. I'm the below ground guy, and then mechanicals kind of take over on that. So I can't answer the question. I'm just not an expert in the best system, best mechanical system in the best setting.
Sure.
Sorry, Raj.
Next question. If cooling is needed even during winter because of heat exchange internally, does the system maximally leverage the external cold weather to cool the buildings?
Well, it's a complex question. So you don't want to take all of the heat out of the field so that at the end of the winter, you're basically heating cold water. So there's a balance. So yes, we are leveraging the heat in the system that we can withdraw, but you don't want to take all the heat out too early because then you're just heating water and your coefficient of performance is 1. You want it to be higher. But they are taking heat out of the system for domestic hot water and for snow melt. So they're balancing where that excess heat. The best way to do that is if you complement your geothermal heat exchange wells with an open water source where you can dump heat or pull heat out faster. That's really what EPIC is doing. And my vision also is in the future is that if our field overheats, I want to say, what if we pull water out of the field with a high capacity well, take the warm out, dump it into a quarry, and then we suck water in from around the field to condition the field to get ready for the summer. So there's operating scenarios that I have up here, but just nobody's given me enough money to test it yet. I don't know if that answered the question, but we got to be very strategic. You want high coefficients of performance. If you take all the heat out at the end of the winter, you're basically heating cold water. You still can do it, but there's that balance that we're always striving for.
All right, next question. Could you elaborate on how the energy payback time was calculated? And are there any factors that could significantly alter that EPT?
So, we use life cycle models. So we know how much energy it takes to produce, transport, and burn 1 kilogram of diesel. We know how much kilograms of diesel it took to run my drillers. Same thing for the plastic in the pipes, the headers, the sand, the bentonite. We get it around the field. So I drew my LCA around the field. because the financial investment for geothermal exchange is what it takes to build the field. Everything else you have to have anyway. So you have to have a distribution system, you have to have chillers and heat pumps. So we drew it around the field, but I'm now going to the operational stage to add that into the life cycle assessment. So right now I drew the box around the field, but we're taking it also to drawing a bigger box around the system.
All right. One more question. So this may not be within the scope of your work with EPIC, but can you say anything about the economics of this campus system, like paybacks, comparison with other systems?
So EPIC is wonderful with data. The one thing that I'm not allowed to convey is price, what they pay for systems. So I'll answer that. Similar systems have financial paybacks of 7 to 10 years. So that $10 million investment for a field, it generally takes 7 to 10 years of energy savings to pay back that financial investment. Same thing for a house. A house in Wisconsin, about 8 to 12 years for the payback. And then it depends if you count the tax credit from the federal government and other things like that. Right now, there's a 30% credit, and you also get more credit if you use domestic material.
8 to 12 years for a
8 to 12 years for a house, yes. 7 to 10 years for a larger system. That's what it is.
I guess it depends on geography of your house.
Sure. Yeah. Basically, bigger houses, the payback is quicker. Smaller, more energy type houses, the payback takes longer because you don't have to use as much energy in the first place.
So collaborate with your neighbors.
Yeah. So the financials say 7 to 10 years of payback. It's good. It's not great. Which is why, and Scott Neeson here is with the industry. It's why the industry also has to push. It's not just the money. It's energy resiliency. It's energy sustainability. All of these other ancillary benefits where geothermal is good at it. Yeah, the finances are important, but it's not everything.
Is this something that could be scaled up to like neighborhood or cities where commercial could complement? Because wouldn't the heat load be larger for residential in the winter time? So
yes.
You could offload some of that heat on the houses?
So that's community geothermal in a nutshell. So in Wisconsin, a resident is exactly opposite. They're heating dominant. So a resident is going to be pulling more heat out of the ground than they're putting in. So if you can connect residences with commercial buildings on a centralized, you're increasing the efficiency of the system. So that would be the goal. Actually, I'm having a student group register for the Department of Energy's Community Geothermal Design Competition. And our project site is going to be the triangle development over by Brittingham Park. So I'm working with the city of Madison, Slipstream. And so what we're doing is our plan is to design a feasible system where we use Brittingham Park for our wells, and then we take that energy and we put it into the it's government assisted housing across the block there. So we applied for a grant for that, but it was not accepted. So it's out there. That's what community geothermal means, a common geothermal field, and then using it communally. Communally. I make up words. I think that's a word. All right.
I think we're over time.
All right. Awesome. Thanks so much.
There was another idea